In this video I'm going to look at Markovnikoff's rule, and as you can see on the whiteboard, this rule helps us to establish the major and minor products of electrophilic addition to unsymmetrical alkenes. So if we think about the unsymmetrical alkene propene, when it reacts with something like HBr, hydrogen bromide, there are actually two possible products. So there's the first one, so that's 2-bromopropane, and what's happened there is the hydrogen has added to this carbon here, carbon number 1, and the bromine has added here at carbon number 2. And of course, if the addition was the other way around, where the hydrogen attached at carbon number 2 and the bromine at number 1, we'd get the product below, 1-bromopropane. So we're going to use Markovnikoff's rule to establish why 2-bromopropane is the major product of this reaction and 1-bromopropane is the minor product. And to do that, we need to look closely at the mechanism. So you can see I've split the board in half. The left hand side, we're going to look at the mechanism in which 1-bromopropane is formed, and on the right hand side of the board we'll look at 2-bromopropane's formation. So if you want to have a go at the mechanism, good practice for the electrophilic addition mechanism, and then we'll go through the mechanism and explain why the 2-bromopropane is actually the major product. So there's both mechanisms drawn up, and you can see that they're very, very similar. The first stage is identical, and so we'll just go through the left hand one. We've got the dipole in the HBr molecule. Remember, bromine's slightly more electronegative than hydrogen, making the dipole this way around. The pi electron pair would be attracted to the slightly positive hydrogen, which will in turn repel the electron pair in the HBr bond completely onto the Br, and therefore breaking this covalent bond by heterolytic fission, and that's because both of the electrons end up going onto the bromine. The hydrogen effectively gets none of the electrons that were in the bond. And so to form the 1-bromopropane, we've put that new hydrogen on this carbon here, and we've produced this carbocation. If we just go over to the other side of the board there, you can see identical process in the first step, but when we get to the carbocation stage, remember the hydrogen is going to go here now, and so there it is there. That means the positive charge is on this middle carbon instead. So since this is where the difference is in the mechanism, these different carbocations, this has got to be where the explanation is for why we get two different products and one is formed in preference to the other. So you can see I've added some extra words there. We've not just got a carbocation here, we've got a primary carbocation. And in this mechanism, we haven't just got a carbocation, we've got a secondary carbocation. So I'll just quickly explain what we mean by primary and secondary. So if we look at this one first, you can see that we've got on the carbon bearing the positive charge, there is one carbon directly attached to that one, whereas in the secondary carbocation, the carbon with the positive charge has got two carbons directly attached. And now for the next bit of information, you can see I've put some green dotted lines around the alkyl groups that are directly attached to the carbons with the positive charge, and you can see in the primary carbocation we have one alkyl group attached to this carbon. This is an ethyl group, whereas in the secondary carbocation we have two alkyl groups attached, and these are both methyl groups. And what you've got to be aware of is the fact that alkyl groups, doesn't matter whether they're ethyl or methyl groups, they are electron releasing. And so what they're going to do is they're going to sort of release electron density towards this positive charge, and what that will do is it will spread the positive charge around the carbocation and actually make the carbocation a little bit more stable if it can spread the charge out. So we've got one alkyl group here releasing its electron density versus two alkyl groups in this one releasing its electron density, and so therefore this secondary one is actually able to spread the positive charge around more than the primary. So the secondary carbocation is more stable than the primary one. So good job, we're nearly finished because this board's getting very, very cluttered now. So hopefully you can still make sense of it. So you can see I've added there the secondary carbocation with its 2 alkyl groups is more stable than the primary one. And then on the left there, the primary carbocation with its 1 alkyl group, remember releasing electron density towards a positive charge, is less stable than the secondary. So the final step of the mechanism, of course, is this bromide ion that's being produced in this heterolytic fission stage. The pair of electrons on the negative charge will be attracted towards the positively charged carbon and form a new covalent bond between the carbon and the bromine. And you can see exactly the same thing happens on the right hand side there. So because the secondary carbocation is more stable, more of it will form, therefore leading to more of this product 2-bromopropane. And obviously the opposite's the case for this one. So we'll summarise the relative stabilities of the different carbocations now. You can see there I've drawn up 3 carbocations, primary, secondary and tertiary. The R group just represents an alkyl group, and you can see those red arrows there, that's trying to show that the alkyl groups are electron releasing or electron donating, you might see in other books. And obviously the more alkyl groups around the carbon with the positive charge, the more that positive charge is spread out, and therefore the carbocation becomes more stable as a result. And so you can see the stability arrow is going to the right, meaning that the tertiary carbocation with its 3 alkyl groups on is the most stable of those 3. And just finally, if we go back to the mechanism for one last time, there's a nice easy trick you can remember to establish which one's going to be a major and minor product. When you've got electrophilic addition to an unsymmetrical alkene like propene, the hydrogen prefers to go to the carbon that has the most hydrogens attached. So you can see this carbon in the double bond has 2 hydrogens, whereas this one only has 1. So more of the hydrogen will go here, producing this secondary carbocation and therefore producing 2-bromopropane, in preference to going to this carbon with only 1 hydrogen attached, leading to the primary carbocation, leading to 1-bromopropane.